Good morning. My name is Noémie Ott. I'm the chair of the Young YEFC. I'm very happy to welcome you for the third day of the Young YEFC CREATE CORRECT summer school that we organized. In this session, we will discuss synchrotron and neutron-related technique. In particular, their use, challenges and perspective for corrosion science and engineering. And I'm very happy to have Seren with us. She works at Paul Scherrer Institute in Switzerland. So Seren, the floor is yours.
Perfect. Okay, good. So, good morning, everyone, and thank you, Noémie, for the introduction. And basically, in my presentation, I briefly introduce some principles of neutron and also X-ray imaging, not synchrotron, but just the commercial lab-based X-ray imaging as an auxiliary to add it to our neutron beam lines. And especially, I'll be focusing on basically, as I said, the instruments at our SynQ facility. So many of you have probably used medical computed tomography or CT scans to look inside the body without doing any surgery. So the same basic idea, meaning rotating an object, taking X-ray or MRI views from many different angles, and then rebuilding or reconstructing a 3D image works just as well for inspecting engineering materials. And I also think that many of us have seen examples of engineering materials where X-ray imaging, X-ray CT scan have been used to reveal features like pore network in foams or in cementitious materials, internal voids or defects in different materials, and much more. And always this is done without, again, cutting the parts to pieces, meaning we do like non-destructive testing. But the problem is X-rays struggle to show light elements hidden behind heavy metals. So that's basically our cue or the reason to bring basically neutrons onto the stage. So that's why in many applications, it's nice to combine neutrons with X-rays because X-rays excel mainly at imaging high Z elements like metals, ceramics, composites, while neutrons are uniquely sensitive to light elements like hydrogenous materials such as water or polymers, even if they're buried deep in metals. So by combining both beams, both modalities, we can capture a fuller picture of multi-phase, multi-material systems. PSI's SynQ is basically one of a handful of world-class neutron user facilities alongside, for instance, ESS and ILL in Europe, ISIS in UK, SNS and NIST in the States, and JPark in Japan, and so many others. And this global network basically gives researchers diverse options for flux, spectrum, and instrumentation. And these user facilities generate basically neutrons by one of two core routes. It could be a fission-based production in a research reactor or spallation in proton-driven targets. Generally, reactor or fission-based sources deliver a bit higher steady-state flux and greater brilliance for imaging. So now looking at each of these mechanisms, basically in fission, basically what happens is a heavy nucleus, like for instance, uranium-235 captures a neutron and becomes an excited compound nucleus. That unstable nucleus then splits into two lighter fission fragments, typically ejecting 2 to 3 neutrons and gamma rays. and the liberated neutrons can also induce further fissions in a so-called chain reaction. But in the spallation, it begins when, again, a high energy projectile, like mainly protons, hit a heavy nucleus like lead, knocking nucleons around in an internuclear cascade and producing pions. This cascade leaves the residual nucleus in a highly excited so-called compound state. So to shed excess energy, this compound at this compound state, it then evaporates many more neutrons and even some protons in a rapid burst, and also the hot remnant emits gamma rays and settles into a lighter, more stable nucleus. And basically, in principle, at SynQ, we use this spallation method. And here you can see like an overview of the construction, which holds the lead target assembly and all the surrounding necessary infrastructure, which basically, I would also like to explain how we produce these neutrons in the first place. So what we do, we start with classic Koch-Roth Walton pre-accelerator. And what happens is first hydrogen gas is fed into an ion source where a hot cathode or RF plasma strips the electrons off the molecules to produce protons. And the Koch-Roth Walton is essentially a voltage multiplier chain that takes a low voltage AC input and boosts it into a steady DC potential of a few hundred kilovolts. That high voltage gap then gives the freshly produced protons their first kick, and before basically they enter the main accelerator. So here's how the main accelerator or the cyclotron looks like. So the ring cyclotron, you can see, injects protons off-center into a magnetic spiral. They are speedily boosted each turn by rhythmic RF kicks. And their passes subtly are wobbled to ensure clear loop spacing, and finally gently peeled off using an electric deflector and guided out for high intensity final neutron production. And this is again that construction that I showed you before, where it contains the lead target. And those energetic protons basically are then transported to hit, to strike the lead target and make spallation possible. And the produced neutrons are then also channeled through moderators and then neutron guides to different beamlines. And basically here are the SynQ different beamlines. SynQ's target hulls, which are in the SynQ's target hull. Basically, this is the target that we talked about, and then around it there are different beamlines. But the main beamlines that we're going to be talking about are the imaging beamlines, and they are basically two important beamlines where they produce thermal neutrons in the beamline called neutra, and cold neutrons in an instrument called icon. And basically, thermal beamlines use neutrons in equilibrium with room temperature moderators, which could be like a room temperature deuterium as moderator. And while the cold beamline uses neutrons further slowed by cryogenic moderators, basically to a bit lower energies. And basically their spectra also mirrors their cold versus thermal nature. So as you can see, icon's spectrum is shifted to lower energies, in principle, as we said, cold neutrons, while neutral peaks at higher room temperature energies, thermal neutrons. So far, basically, we've only focused on neutron production and beamlines, but here at Tsinghua, as I mentioned, we've also integrated lab-based X-ray imaging using commercial tube sources, as you can see in this figure. And as you may know, the mechanism at which the X-rays are produced is that a heated tungsten filament is basically thermoionically emitting electrons, and they're accelerated onto a metal anode, like a tungsten anode, to produce a cone beam of X-rays. And that beam basically is used for imaging passing through a rotating object again, or a steady object to create images or projections. So, the neutron and X-ray, to be able to combine them, basically at Tsinghua at different beamlines, we've engineered basically flexible ways to mount an auxiliary X-ray tube alongside a neutron beamline. For example, in Neutra we have a coaxial alignment, and at DICOM we have orthogonal crossing, and it could also have any other flexible alignment setup. And each of these setups basically offers like a trade-off in ease of alignment, simultaneous acquisition, and space. So now that we talked about the complementarity of these two methods. Let's look into a bit more details into how these are actually, what is the mechanism behind it that they create different contrast mechanisms. So basically looking at each beam creating different attenuations, or in other words, the way they interact with materials they penetrate or they want to image. So for first starting with neutron matter interaction, basically neutrons interact in principle with three main ways. It could be elastic or inelastic scattering, or it could be radiative capture or absorption in principle. So what happens in elastic scattering is that neutrons collide with nuclei and basically bounce off, losing some of their kinetic energy, and they most efficiently do so on light elements like hydrogenous materials or lithium. And so basically hydrogen-rich materials can appear strongly attenuating if you do like a projection or even a tomography. But in elastic scattering, neutrons basically excite nuclei to a bit to higher energy and higher energy states, and basically exit with a bit more reduced energy. And the excited nucleus basically emits also gamma rays, adding energy-dependent attenuation. This mainly works better like for isotopes and so on. And then we have this radiative captures, which basically neutrons are absorbed mainly by nuclei, and then again excited, and then mainly emit gamma rays. But coming now to the X-rays, how they interact with matter is that X-rays undergo, for example, a photoelectric effect, Compton scattering, or pair production at some with higher energies. So in photoelectric effect, basically what happens is a low to mid-energy X-ray photon is basically completely absorbed by a tightly bound orbital electron, ejecting it and basically creating an inner shell vacancy, and then another electron dropping releases energy. And then basically this is common in higher Z atoms, which have more electrons, and basically they exhibit more photoelectric effect. And Compton scattering happens at a bit intermediate energy levels of X-ray spectrum, and X-ray photons scatter off loosely bond nearly free electrons, transferring part of its own energy to electron and emerging at a bit lower energy and altered direction, of course, and producing a continuum of scattered photons. And this is the most common basically thing that happens, which is like basically the contrast mechanism. And we can also have pair production, which happens really at higher energy levels, and the photon can basically convert this energy in the nuclear field into electron-positron pair. And so based on these two different mechanisms, so we can see that since neutrons and X-rays basically interact with matter in fundamentally different ways, so X-rays, again, I'm summarizing, primarily basically engage with the electron cloud that grow rapidly with the atomic number. So, but neutrons, by contrast, interact directly with atom nuclei via elastic scattering, which is mostly effective in light nuclei, as I mentioned, and in elastic scattering and basically absorption. Because of these different mechanisms, X-ray attenuation increases monotonically with Z number. Heavy elements in principle, such as lead, absorb and scatter X-rays for more strong, very strongly than the light elements, while neutron attenuation peaks at few neutron-hungry light nuclei and remains low for most heavy elements. So the result is that, as you can see, this kind of Morris reversed bubble or sphere chart for the neutron attenuation. So this highlights again why combining both beams reveals a fuller picture, or they are like a complementary information about the materials. But so let's look at now how in practice an imaging beamline looks like and how we in practice do this imaging. But here, by the way, I'm only showing the neutron imaging setup. But of course, next to it, perpendicular or in parallel, there could be also an auxiliary X-ray source. And basically to image with neutrons, we use like such a simplified detector system, as you can see in the right-hand side. And in principle, it has three components: a scintillator, like a 45-degree tilted mirror, and a camera setup, like a lens with a CCD coupled camera. And basically what happens that this scintillator, which could be like a gadok scintillator, like gallium oxysulfate, which basically transforms the neutrons into the visible light, and then the visible light is basically reflected with this 45-degree mirror into the lens coupled CCD camera, for example. So this is like the technicality behind how we capture the image, but the physics behind it, basically in principle, what gets translated, how the image forms basically into the basically how this what gets translated into the image intensity, or what we see in the captured image as any beam of initial intensity I0 basically passes through material. Would be like a heterogeneous or homogeneous, that doesn't matter, but let's say we have a material with a thickness X, then the transmitted intensity I will follow the Beer-Lambert law, where basically the mu is the linear attenuation coefficient of the cross section that we are basically looking for. Basically, in practice, all those different beam matter interaction that we discussed about neutron and X-ray in each modality of imaging contributes basically to the image contrast or attenuation, image formation in principle. So this simple law also underpins the reconstruction algorithm. So everything is now based on this concept that our image formation mechanism is following this Beer-Lambert law. And basically that's how we can map the thicknesses or the compositions into gray value changes in the tomograms or in the projections. But now speaking about, now that we talked about the image formation, so image formation in principle is done in 2D. Whatever, basically we have a 2D detector, but depending on if we rotate the sample or not, we can have like a simple 2D image or we can have a tomography. But projection, this 2D image is called projection. Projection images basically what they do, they in principle superimpose all internal features along the beam paths. And like make an integral or like a average image in on the detector, but what then tomography does is that tomography tries to solve this superimposition by rotating the sample, acquiring several projections at several angles, and then mathematically untangling them into true cross sections or linear attenuation coefficients. But now let's take a closer look at the tomography or reconstruction method. So here I'm just showing like a simple 2D example, but then even if this object was like 3D, like imagine this is a 3D object extruding through your screen. So we're going to do the same thing in principle for every height of it, so at Z direction. Basically, just now speaking for this one cross section. So what happens is that as the sample basically rotates, each projection basically records how much of the beam is absorbed or attenuated along every ray path, and all of these one-dimensional, because this is a 2D problem, one-dimensional profiles are stacked side by side to form the sinogram, as you can see here, which is a 2D map in which each row corresponds to a particular rotation angle and each column to one detector channel or one detector pixel. So, and then features in the object trace out smooth curves in this sinogram. So in one of the important or like very well-known reconstruction methods is filtered back projection. So we basically project and we can smear back to reconstruct the object. But in filtered back projection, we first pass each projection through a high pass filter to correct for the fact that like the if we did just simple back projection alone, as you can see in this figure, then we will overweigh the low frequency components. So once filtered, we can smear safely back each profile across the image volume along the same angles that the projections were acquired. And by basically summing all of those back projected profiles, and also filtered profiles, the overlapping contributions basically reinforce the true structures or and basically cancel out any blurs and yield a sharp sharp quantitative cross-section information, or let's say linear coefficients, which is linked to the material properties of the object. So basically now, after this a little bit of a short summary of how we can how basically each of these techniques have different attenuation mechanisms, how they can form the image, and how we can do a tomography. I would like to show you like some real-world examples, especially the examples that I usually work on them. So basically, this is like an application where, again, both neutrons and X-ray tomography work together to reveal both microstructure and also important features like homogeneous materials. And my example is basically steel corrosion in steel reinforced concrete sample. And basically what neutron imaging can show is the corrosion products, for instance, and moisture ingress in the cement matrix. X-ray imaging, for example, can clearly delineate, show the, for example, steel, denser material, the structure, the pore space, and the concrete microstructure. And by combining both, we can then better track where and how corrosion evolves. So this is like a example image. So like a cross only. These are the two reconstructed tomograms. And in the left-hand side, you can see like for example, somewhere in the middle of the sample. Imagine this is a full 3D stack of images reconstructed. I'm only showing one example slice of it. And you can see that with X-ray tomogram and with neutron, we can see more or less different, like rather completely different like contrast mechanisms of the same object. And these samples, these objects are also digitally registered. So we are seeing exactly the same regions with the help of both modalities. And as you can see, for example, our sample has aggregates. For instance, X-ray image does not show them, but with neutron image we can see. So we can see, visualize the corrosion products much better. And also in the cement paste, as you can see, we can visualize like the background moisture levels better than, but basically it's in principle it's impossible with the X-ray image. And then because we have a 3D full tomogram of our object, then we can also segment out the features of interest. For instance, I have here segmented the steel bar, and then like steel loss, which like we call them pitting, for example, and then also corrosion products, for example. Then you can do all sorts of, after you basically delineated your features of interest, segmented them out, one can do all sorts of statistical analysis, like doing computing the volumes, the profiles across the length of the steel, and similar things. Another example in which it is absolutely basically needed to use neutron imaging is another case study for corrosion samples, which are basically archaeological nails, which are abundantly available, and we use them to study long-term corrosion. And we choose them because they're just abundantly available, and we can even do sometimes post-mortem or like basically destructive analysis, like cut the cross sections and also cross-correlate with neutron tomograms, like the X-ray and neutron tomograms. And for example, in this case, you can see these are X-ray cross-sections, these are neutron tomogram slices or cross-sections. And with X-ray, we can clearly identify like the remaining iron core, whereas with neutron imaging, the iron is not clearly visible. It's more or less in the same range of other, like soil, for instance. So it's really hard to differentiate where the core is unless we did X-ray tomography as well, in addition to the neutron tomography. And again, we can, with these bimodal images, we can use, for instance, a bivariate histogram of 2 tomograms to bimodal clustering to segment out different features of interest. So similar to the previous case. So, but beyond the examples that I mainly work with, so as also I mentioned here and there, so the neutron image, or the neutron image, mainly neutron image, and also could be coupled with X-ray image, can basically be used for different other applications in which we want to track, identify, or quantify heterogeneous materials like or lithium, other light elements. So this has, like for example, implications, for instance, in hydrogen embrittlement, in which we can basically directly visualize hydrogen and its accumulation sites. And then we can also, if we have calibration samples with known amounts of hydrogen doping, we can also quantitatively measure the hydrogen levels, the hydrogen amounts. And other relevant engineering applications that we usually encounter in our group are, for instance, fuel cells, like for proton exchange membrane fuel cells, mainly for moisture movement, moisture transport, lithium-ion batteries, of course, for tracking the lithium distributions. And also there are many examples for additive manufacturing. This is usually for strain analysis, but also imaging are also interesting to see the defects, for instance. And then, of course, fluid flow and porous media, we also do it in our concrete samples, for example, or in like this for soil physics people. This is a very interesting topic. And also the quality control in manufacturing, especially for very dense metallic objects that's otherwise impossible to penetrate through with X-rays. Basically, like imagine you have a big object of steel that's going to be really difficult to inspect with X-rays, but with neutrons, it's nothing basically for neutrons to image such objects. So in conclusion, basically what I would, how I would summarize this is basically that basically the true power of neutron imaging is usually realized when we can really see that what X-rays cannot do, but neutrons can do. So basically, this is even highlighted more. And it's a very powerful method in principle. And it even has, as I mentioned several times, this because of its unique material contrast, it allows us to trace light elements that are otherwise impossible with other modalities. And of course, heavy metals, it's the best tool for non-destructive inspections and basically different research applications. And in principle, I also, so in addition to the introduction to the neutron imaging itself, I also wanted to shortly, very quickly introduce you to our how you can basically access our instrument. Maybe many of you know, but just for those who may not be aware. So if you like to experiment with your own samples at basically at SynQ, so you can first visit our Duo system, our user office website, And basically you can log in and create your account, and also you can follow where the proposal calls are. And usually, if it's your first time applying for the beam time, it's really nice to have some early discussions with some of our beamline instrument scientists, as you can see their names here. Which is really beneficial to ensure you get your optimal setup, and basically you can fulfill the requirements of your research properly. And you can also have a successful proposal writing and application and approval. So by this, I would like to thank you for your attention and would be happy to hear your questions.